So the seventh question asks us to find the set of points where function f of x is equal to x by 1 plus mod x is differentiable. Okay, so yes, how do we find out if a function is differentiable or not? As in, which points is a function particularly indifferentiable?
When we have to find whether a function is differentiable or not, we basically have two main steps.
Okay.
The first one is, if we know that the function is continuous, we can directly differentiate and check that f dash a minus equals to f dash a plus, which is a finite value. Then we can conclude that a function of x is differentiable at x equals to a.
Okay.
Or else if we don't know whether it's continuous or not, then we have to use first principle, which is limit h tends to 0 plus function of a plus h minus function of a divided by h equals to function of h tends to 0 plus function of a minus h minus function of a divided by minus h, which should be equals to a finite value.
Okay, again, this should be equal to a finite value. So basically, the first principle states that this limit, the left hand limit, this should be equal to this limit, and also it should be a finite value, and then and only then is the function differentiable at x equals to a. Right?
Exactly.
Right. So which method are we employing right now?
In this question, we are going to prove that the function is continuous and then
use it, right?
Exactly.
Okay, cool.
So the best method to prove that a function is continuous or not is to draw the graph of the function.
Okay.
Okay. So I'm going to tell you some basic tricks and techniques which will help you draw any type of functions graph. Okay, so there are 2 points that we have to keep in our mind when we need to plot a graph of a function.
Okay.
So the first one is checking the value of x where numerator is 0, denominator gets 0, and where f dash x gets 0.
Okay.
And the second point is finding the value of function at x equals to 0, at x equals to plus infinity, and x equals to minus infinity.
Fine. So these are the 2 points which we need to find and to prove that the function is continuous.
Exactly.
Cool.
Now moving ahead, we have a modulus function in the given function to us.
Okay, so we split it up into these 2 parts where x is greater than or equal to 0 or x is less than or equal.
Exactly, because whenever we have a modulus function, the first step should be simplifying it.
Right.
And how do we get x greater than 0, x less than 0? Because we know that it is mod x, so it has a critical point at x equals to 0. So we choose that x equals to 0 as a point of splitting the function.
Okay.
Okay, so moving ahead, we take the first part, which is the domain, which is x greater than or equals to 0. We have a function fx equals to x upon 1 plus x. Okay, going by the technique, we find the value of function at x equals to 0. The function value comes out to be 0. At the x equals to infinity, the function value comes out to be 1.
Yes.
Because both numerator and denominator has degree of x equals to 1.
Exactly.
So we divide it by x, and we place limit 1 by x and x tending to infinity equals to 0.
Right. That's a usual method we use when we have the same degree of both the numerator and the denominator, right?
Exactly.
We divide. Yes.
So moving ahead, we know the value of function at x equals to 0 and x equals to infinity.
Yes.
We won't be checking the value of function at x equals to minus infinity, as it's not in our domain.
Okay.
Now going to second step, which is finding value of x when numerator equals to 0, that is x equals to 0, denominator equals to 0, at x equals to minus 1. Again, we won't care about this because it's not in our domain.
Right.
When we find out f dash x, it comes out equals to 1 upon 1 plus x square. Okay, so it's always increasing.
Obviously, because the denominator is a square number and it's always positive.
Exactly. So we won't get f dash equal to 0 for any point for x greater than or equals to 0.
Right.
Okay, so now when we are plotting the graph, we use these points to actually get help. So when x equals to 0, we know that the function of is at 0, and when x tends to infinity, the function tends to 1.
Yes.
Okay, and since we know that f dash x is not getting equals to 0, so it will be a smooth curve. Also, since denominator is not 0 at any point, so we know that the function will be defined throughout the domain. Okay, so we can smoothly join the curve.
Right.
On joining the curve, we get a smooth curve, and similarly applying the same steps for x less than 0, we get the desired graph.
Right. So this is the desired graph, right?
Exactly.
Right.
So since we have the graph, we can directly comment on the continuity of the function at x equals to 0. Looking into the graph, we can say that it's continuous at x equals to 0.
Exactly. So looking at the graph, it's pretty simple and obvious that x equal to 0 is continuous.
Exactly. Now moving ahead, we have splitted the function in x greater than 0 and x less than 0. So what we are going to do next is like we are directly going to differentiate and check the differentiability at x equals to 0.
Right.
So we find f dash 0 plus and f dash 0 minus, and it comes out that both of them are equals to 1, which is a finite value. So we can conclude that it's a differentiable function.
Right. So it's it is a differentiable function, and the set of points where function f of x is differentiable is all points, in fact, as we see the graph, and is continuous throughout the domain. Am I right?
Exactly.
Right. So this was question number 7, where all the points in the graph of f of x equals x by 1 plus mod x was continuous as well as differentiable. So question number 8 tells us and defines a function f of x as 4 plus sine 2x plus a sine x plus b cos x whole divided by x square. So the question is, if limit as x tends to 0 f of x exists and is finite, find a and b and the limit. Okay, so how do we approach this problem from the beginning?
Okay, so since we are given with the fx, okay, so looking into the denominator, which is x square, so when x tends to 0, our denominator also tends to 0.
Yes, definitely.
So since it's given that limit x tends to 0, fx is a finite value.
Right.
So it will be only possible when when the given expression is an indeterminate form.
Exactly.
So since we know that denominator is 0, so we know that our numerator has to be 0. Okay, so we know that at x tends to 0, our numerator is also 0.
Yes,
so
pretty much.
Applying this in the numerator, we get 4 plus 0 plus a into 0 plus b into 1 equals to 0.
Yes. So we have 4 plus b equals 0, which says b equals minus 4.
Exactly.
Right.
So now we are aware with the value of b. So since we know that limit exists and it's 0 by 0 format, so we can apply L'Hospital rule.
Oh, right. Yes, L'Hospital rule will come handy when 0 by 0 format is there, and it splits our work into very, very simple.
Exactly, but we must always keep in mind that the function involved is a completely differentiable function, and we can see that sine 2x, sin x, cos x, x square are differentiable at x equals to 0.
Yeah, definitely. Yeah, okay. So you're mentioning that is also a condition which has to imply for us to apply L'Hospital rule.
Very true.
Okay, so the two things are, one, it has to be 0 by 0, and two, that whatever functions are there in the numerator and the denominator should be differentiable at that point on the graph.
Definitely, it can also be infinite by infinite, because when we substitute, it gets 0 by 0. So either it should be 0 by 0 or infinity by infinity.
Right. So in this case, let's apply L'Hospital rule.
Okay, so when we apply L'Hospital rule,
limit as x tends to 0 would become 4 plus sine 2x, 2 cos 2x plus a cos x minus b sin x whole divided by 2x.
Exactly.
Right.
Okay, so again looking when x tends to 0, our denominator is equals to 0, and we know that this limit is existing and is finite, so we can conclude that it should be 0 by 0 format.
Definitely.
So the numerator is also 0, so we can see that 2 plus a equals to 0.
Yes, so a is minus 2.
Exactly, so now we have the value of b as well as a with us.
Exactly.
Okay, so now moving into the next step, we can see that it's again 0 by 0 format, and cos 2x, cos x, sin x and x are differentiable at x equals to 0.
Right.
So again the L'Hospital conditions holds. So again we are going to be applying the L'Hospital condition over here.
Definitely.
So we differentiate it and we get limit x tends to 0
minus
minus 4 times sin 2x minus a sin x minus b cos x.
Right, exactly.
Okay.
Right.
So
This is no longer in the 0 by 0 format.
exactly, it's looking into the denominator, which is like finite value.
Exactly.
So
now let's just substitute the value.
exactly, now it becomes minus b by 2. Since value of b is known, it becomes minus 4 into minus whole divide by 2. So limit is equals to 2.
Okay. So this was a pretty simple question as such, but slightly lengthy in procedure. But let's just recapitulate what happened over here. So initially we found out that the denominator is equal to x square, and it was in a 0 by 0 format. But the numerator had, if x tends to 0, then the denominator tends to 0, and x tends to 0, numerator also has to tend to 0. So we found out when we substituted x equals 0 in the denominator that b is equal to minus 4. And once we got the value of b, we kept it aside, and we also noticed that the numerator and denominator with respect to x equals 0 as a point fall under the L'Hospital rule. So we applied the L'Hospital rule, and in fact we applied the L'Hospital rule twice, and we in fact found out that the value of a is equal to minus 2. Similarly, as we found out the value of b. Right. So as soon as we had the value of a and b, we had no difficulty in solving our limit. We substituted the values of a, b, and also substituted x as 0, and we found out that the limit of the function at x tending to 0 is equal to 2 as required. So this is the question number 8. Right, so we have question number 9 over here, which asks us to find function of pi by 4 and comment on continuity at x equals 0. While they've given us that f of x is equal to limit as n tends to infinity 1 whole divided by 1 plus n sine square x. Right, so how do we start off with this question?
Okay, so we see this expression. Okay, so whenever we have to find a value of something and the value of x is given to us, we don't have to get confused. We just directly place the value into the expression that is given to us.
Okay.
So it turns out to be n times 1 by root 2 whole square. Okay. So now we can see that since limit n tends to infinity, denominator tends to infinity, whereas numerator is constant. So we get the value of function of pi by 4 equals to 1 by 1 plus infinity.
Yeah, so it's 1 by infinity
which
form.
Equals to 0.
Exactly.
Okay, so now the main part comes checking the continuity of function at x equals to 0.
Okay.
So how are we going to check the continuity of function at x equals to 0? So we are going to apply the basic principle. So the basic principle states that if limit x tends to a, f of x equals to value of function at x equals to a, then it's a continuous function.
Okay, right.
Continuous at x equals to a.
Right.
Okay. So now since we are checking continuity at x equals to 0, first we find the value of function of 0. So what we do, we place x equals to 0 in the expression. So we get limit n tending to infinity 1 upon 1 plus n times 0.
Exactly.
Though n is tending to infinity, we have an exact 0 over here.
Okay.
So 0, exact 0 into infinity will give us 0. Just the very same way 1 into exact infinity gave us 1.
Okay. So basically
what is this? 0 into 0 into 0. But since this is an exact 0, its value will be 0.
Exactly.
Okay, so moving ahead with this question, we get f of 0. F of 0 equals to 1.
Yes, definitely. 1 by 1 is 1. Yes, exactly.
Okay, so now we have to check limit f of x when x tends to 0. Okay, so applying this, we get limit x tends to 0 1 upon 1 plus n times sine square x, also limit n tending to infinity. Okay,
Exactly. Yeah.
So n tends to infinity, and sine square x tends to 0
Yes.
as x tends to 0.
True. As x tends to 0, sine square x tends to 0. Yes.
Okay, so sine square x can be treated as delta.
Yes.
Okay, and which is very small quantity compared to 1. So delta times n, which is delta times infinity, tends to 0. Because delta is a very small quantity.
True.
Because delta is x square. Okay.
Yeah.
So x square its power is 2, whereas n the power is 1. So the overall quantity will tend to 0.
Okay. Right.
Okay. So applying this concept, we get limit x tends to 0. F of x will become 1 plus 0, which is equals to 1. Okay, so we can conclude that since limit x tends to 0, f of x equals to function of 0, so it is a continuous function.
Right. So so we made sure we proved that it's a continuous function. So firstly we had to find out f of pi by 4. So have we found out f of pi by 4 yet? Yes, we have. Limit of n tending to infinity and the function over here, which becomes 0. So effectively f of pi by 4 is equal to 0. So this was the first part of our solution over here, right? And the second part was for us to comment on the continuity of the function at x equals 0. And after a lot of deductions and assessments, we found out that limit of x tending to 0 f of x is equal to f of 0. And what does that mean? That means that f of x is definitely continuous at x equals 0.
Exactly.
Right. So this was question number 9. So coming to the 10th question, we have f of x be polynomial of degree 4 with roots 1, 2, 3 and 4 and leading coefficient 1. So what does leading coefficient mean exactly?
Leading coefficient means, like, let me explain you what a quadratic function is like. Let quadratic function qx be equals to a0 x raised to n plus a1 x raised to n minus 1, so on till a n minus 1 x raised to 1 plus an.
Right.
Okay. So now this quadratic equation can also be written in the form of a0 dash into x minus alpha, x minus beta, so on till x minus gamma.
Right.
Where alpha, beta, gamma and so on are its roots of the quadratic equation. Okay, and now we have to find the leading coefficient. So collecting coefficients, we get a0 dash 1 from here, 1 from here and so on. This is equals to a0. Okay.
Right.
So we can conclude that the leading coefficient a0 dash equals to a0. So leading coefficient is the coefficient of x raised to n.
Okay. So leading coefficient is basically the coefficient of the highest power of x in any equation whatsoever, right?
Yeah, very true.
Okay. So continuing the question, g of x be polynomial of degree 4 with roots 1, half, 1 by 3 and a quarter with leading coefficient 1. So find limit x tending to 1 as of f of x by g of x.
Okay, so just now I have discussed some concepts of quadratic. So that's the main crux of this question. Since we know the leading coefficients and the roots, we can get the quadratic equation.
Okay.
So our equation f of x becomes leading coefficient, which is 1, into its x minus alpha, which is 1,
right,
x minus beta, which is 2, so on till x minus 4.
Yes.
And g of x becomes 1 times x minus 1, x minus 1 by 2 and so on till x minus 1 by 4.
Exactly.
Okay. So now in the question we have to find limit x tends to 1 f of x
by g of x.
By g of x. So it becomes limit x tends to 1 x minus 1 x minus 2
x minus into x minus 4 divided by x minus 1 into x minus half into x minus 1 by 3 into x minus 1 by 4.
Exactly. So the factor that was creating indeterminate form, that is 0 by 0, is x minus 1 in both numerator and denominator.
Yes.
So we can cancel both of them.
Okay.
So now the indeterminate form has vanished.
Right.
We have a non-0 by 0 format.
Right.
So we can directly apply limit over here.
Brilliant.
So now we are left with minus 1 into minus 2 into minus 3 divided by minus 1 by 2 minus 2 by 3 into minus 3 by 4.
Perfect.
So on simplifying this, we get 2 times 3 times 4. So this is our limit, which is equals to 24.
Exactly. Right, so this was pretty simple as such, as in we just needed to know the meaning of what we call a leading coefficient. So once we found out what a leading coefficient means, we got f of x and g of x in their respective forms from the given data in the question, right? So as soon as we found out this, this is one data, and also since this are the roots, they'll become x minus 1, x minus 2. But then how do we know how many roots are there? So we made sure that there were 4 roots by seeing that the polynomials were of degree 4, right? So
exactly.
As soon as that was done, it was pretty simple for us, and the job was pretty much done. And so the limit of x tending to 1, f of x by g of x would simplify, and x minus 1 was the only term which was introducing a 0 by 0 format, and as soon as that was cancelled, we could immediately arrive at the answer as 24 as the limit. So this is question number 10.